Welcome back. So, in our last exciting episode, we were talking about alternating series, which are series where one term is positive, then one term is negative, then positive, then negative. The signs alternate. Those are actually pretty easy to check if they converge. Right? We just see if the numbers that we're adding or subtracting are decreasing and going to zero. That's much easier to check, and it's also much easier for them to converge. For example, if we look at the examples we had last time, maybe this first one, often called the alternating harmonic series, because of course it's the sum of 1 over k. Well, by itself that'd be the harmonic series. With the negative 1 there, that makes it the negative 1 to the k. That makes the sign switch back and forth. So it's an alternating series, and in this case, because of the 1 over k, we call it the alternating harmonic series. If the alternator wasn't there, we just have the harmonic series and it would diverge. But if we put in the negative 1 to the k to make the sign switch back and forth, it will converge by our alternating series test. So we need a way to describe the difference between series like this one that converge because it has help, because half the terms are negative, so we're subtracting as much as we're adding. So that's one possibility of series converging, but it's kind of a faker, right? It's converging because it has help, because half the terms are negative. So if we had a series like negative 1 to the k and then 1 over k squared, p series with p equal to 2, that would converge even without the negative 1 to the k. So we need a way to tell the two apart. And so our first definition will do that. A series will converge absolutely if it converges when you make all the terms positive. So the reason we say converges absolutely is not that we're really certain about it. That it absolutely converges. what we mean is it converges if we make all the terms positive. The way you write that is to put absolute values around all the terms, right? That's how you would write make all the terms positive, is you put absolute values around the AK. So a series AK will converge absolutely if the sum with absolute values around it converges. Absolute values around each term. So that's great, right? So that gives us a way to say if it converges absolutely, then it really, really, really does converge, even if all the terms were positive. So those are sort of the real deal, right? What about the fakey ones, right? Well, if we have a series that converges, but not absolutely. So a great example is that alternating harmonic series. It converged because it was alternating. But without the alternator, right, if we made all the terms positive, we just have the harmonic series, and it wouldn't converge. So if we have a series that converges, but not absolutely, again, like the alternating harmonic series, then we say it converges conditionally. Again, sort of the words aren't necessarily great. I mean, converges absolutely makes it sound like we weren't sure about all the other ones converging, right? But converging absolutely has to do with the absolute values, right? Converging conditionally, why do you call it conditionally? Well, it's sort of that the condition is that half the terms be negative, right? That's what the conditionally is. It's converging because of the help it's getting from half its terms being negative. Well, I say half. These definitions apply even if we're not talking about a harmonic series. And we'll see some of these in the homework, where we just have a series with a whole bunch of negative terms. Infinitely many of the terms are negative, infinitely many of them are positive. They don't have to alternate for this definition to make sense. Okay, let's do some examples. So here is negative 1 to the k and 1 over k squared. Right? Well, if we try the alternating series test, which would be, of course, the obvious thing to try, where we put our thumb over the sum and over the alternator, and we just look at the sequence, 1 over k squared. The alternating series test says we just have to check. Is that decreasing? Yeah. Is it going to 0? Duh. So this is clearly going to converge by the alternating series test. But does it converge absolutely or not? Right? Well, that would be like just putting your thumb over the alternator. So if I ignore this part, right, and I look at the sum of absolute value of 1 over k squared, in other words, ignoring the minuses, so I have the sum of 1 over k squared by itself, that would be a p series with p equal to 2. That guy converges, so this series converges absolutely. It converges even if I put absolute values around the whole thing. Okay? Next up, well, this is the one we've been talking about already, alternating harmonic series, right? So the sum of -1 to the k and then 1 over k. Again, this will converge because if I look at the 1 over k sequence by itself, that's decreasing, goes to 0, alternating series test says it converges. But if I take out the alternator, I've got the sum of just 1 over k. That's the harmonic series, and it diverges. So what I have left converges, but not absolutely. So it converges conditionally. So let's think a little bit more carefully about the steps we went through when we worked this problem. If we look back at the sum of -1 to the k and then 1 over k squared. So I thought to myself the following thoughts. Oh, wow, that looks like an alternating series. Yay, it's easy. Alternating series test is what I need to do. How do I do the alternating series test? I completely ignore, right, the sum and the -1 to the k, and I just look at the sequence. Right? Remember, we made a huge deal out of keeping straight the difference between a sequence, the list, and the series, which is the sum. I just look at the sequence, 1 over k squared. And if that goes to 0 and is decreasing, ding, 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 we're done. Alternating series test says the entire series, the way it's written, with the alternator and all, will converge. And I get that by just looking at the sequence. Okay. Next up, I want to see if it converges absolutely. Well, that means looking at the series 1 over k squared. In other words, I put absolute values around this whole thing, which essentially means ignoring the alternator. In other words, treating this as though all the terms were positive. So it means I'm looking at not the sequence 1 over k squared, but the series, the sum and the 1 over k squared together. So first step was it's alternating, so I just look at the sequence 1 over k squared. It went to 0. We're done by the alternating series test. Now I look at the series 1 over k squared, and I do whatever I have to do to see whether that converges or not. All right, we're back to sort of hand-to-hand combat with this sequence, this series, to see what it does. And any of the tests we've used before may be what we have to use. In this example, it's easy because it's a p series, p equal to 2, so it's going to converge. That trips the switch that says we converge absolutely. Okay? So again, what's the process when you see an alternating series? First, I look at the sequence. Is it decreasing and going to 0? Yes, in this case. If it wasn't, then of course it would diverge because of the divergence test. But if I just look at this sequence, it's decreasing, it goes to 0. That's the first step. If that happens, then I know my entire series will at least converge. Then I look at the series, okay, 1 over k, where my pointer is for this bottom one. The series, if it converges, then I converge absolutely. If it doesn't, I only converge conditionally. Okay, let's look at something that's not alternating. I mentioned that the definition of conditional convergence and absolute convergence didn't require that we have an alternating series, just that, it makes sense to talk about whenever some of the terms are positive or negative. In fact, it makes sense to talk about it even if all the terms are positive. It's just really boring then because all of the series that we were doing back in the other sections with the alternating with the comparison test, with the ratio test, the root test, where all the terms were positive, all those were converging absolutely. We just never bothered to say it because they all were converging absolutely. There was no conditional to it because none of the terms were ever negative. In this example, wow, I got cosine of k. What in the world happens if I start plugging 1, 2, 3, 4, 5, 6 into cosine? Well, cosine will always give us a number between -1 and 1. And when I start plugging in integers, 1, 2, 3, 4, 5, again, notice this is in radians. So 1 radian, 2 radians, 3 radians, and so on. I'm going to get some numbers that are positive, some numbers that are negative, and they're just going to bounce around all over the place. So there isn't a nice plus minus, plus minus, plus minus pattern. So just some of them are positive, some of them are negative. Wow. Okay. This kind of example shows up a lot. You'll see this very often in the homework. And the trick for something like this, especially when you see a sine or a cosine, it's usually sitting there going, hi, I'm here and I'm less than 1 and bigger than -1. So I'm just sort of here to randomly spew out minus signs. So rather than try any of the tests that we know before, which don't work, right? Limit comparison test, ratio test, root test, they don't work because integral test, because some of the terms are negative, so they don't work. It's not an alternating series test because, again, some of the signs are positive, some of the signs are negative, but they don't alternate plus minus plus minus. They're just some are positive and some are negative. So what do we do? Well, the trick is let's just check from the very beginning and see if it converges absolutely, right? So what we hope is if we just put absolute values around this thing, that it will still converge, in which case it converges absolutely. And well, if it converges absolutely, it absolutely converges, right? It will definitely converge and we're done. And in this case, it's pretty easy because the absolute value of cosine is always less than 1. So absolute value of cosine of k over k squared is always less than or equal to 1 over k squared. Okay, well, so what I'm really doing here is the direct comparison test, right? The series that, because with the absolute values around it, all the terms are positive. So the absolute value of cosine k over k squared, that's the smaller sequence, right? When I compare that to 1 over k squared. When I add up the sequence 1 over k squared and get a series 1 over k squared, it converges, p series with p equal to 2. So the original sequence that I started with converges absolutely because it converges when I put absolute values around all the terms. Now, if this hadn't worked, right? If the absolute value trick around it hadn't converged, then well, but usually doesn't happen, right? Because there's usually not a good way to play with this unless something like this happens. Okay. One more bit about how important it is for the terms to be positive and negative and so forth. If you think back to things like the ratio test and the root test and the um, integral test and all those various tests, they required that all the terms be positive. Okay, our textbook will at this point list 2 more tests, a generalized ratio test and the same way they do a generalized root test. And all it means is this: slap absolute values around it, okay, around the sequence that we're adding up. Slap absolute values around the AK. And then do the ratio test. Right? If it converges, then the original converged absolutely, just like in that last example. You could play the same game with the root test. Okay? Slap absolute values around it, then do the root test. If that converges with the absolute values in there, then it'll converge absolutely. Why do they even bother to say this? Well, because, it's a textbook and they always say everything. But we'll need this idea when we get to power series, right? In a video to come very shortly for you. Whatever those power series things are, and you've heard me say that word in some earlier videos, we'll need this idea of, hey, let's just slap absolute values around it, then do the test. Right? That'll happen a little bit more later, and we'll need that idea. So that's why they say it here. This is one reason why when you start listing out tests, there are several of them, but the book acts like there's even many more because they state generalized in front of several of them and give you even more tests.